Hello, everybody. Welcome to Embracing Ruby Magic, Statically Analyzing DSLs. My name is Vinny. I'm a member of the Ruby Developer Experience team at Shopify. We work with all sorts of developer tooling. One aspect that we work with a lot is static analysis and type checking, which is what I'm going to be talking to you about today in the context of the Ruby LSP. If you want to know a little bit more about me and my work, you can find me at Vinicius Stock. And if you would like to know more about the work that our team does, I highly recommend you check out the talks from my colleagues. Alex Momchalov is going to be talking about how we migrated the RBS parser to be made in pure C with no dependencies regarding the internals of Ruby and the VM. And then Alex Tejaza is going to be talking about the RBS support that we are pushing forward in Sorbet via comment annotations. And if you would like to work with us, we have positions open. You can scan the QR code and land on the link where you can apply, or just come talk to any of us in the conference, in the after party, whenever. So to start, we need to first define what is static analysis and what are DSLs. And in the context of Ruby, the best way that I can put static analysis in a single sentence is that it is a technique to try to predict what will happen in a program before you actually executing it, without actually executing it. There are several tools that are enabled by static analysis, many of them in an editor context, like every single LSP feature, every single language server feature, go to definition, showing information on hover, or showing completion suggestions. But it's not only limited to the editor. You can also have static analysis-related features that exist in other contexts. For example, we have at Shopify a system that can detect dead code and then open PRs automatically to remove it. But you can also have other things, such as code-based visualizations that will allow you to see your code base in a more high level. Before we move on to defining DSLs, I also want to mention, well, why would we try to predict what the code's going to do instead of just executing the code and then actually seeing what is happening? There are a few reasons for that, but the most critical ones, in my opinion, are the fact that executing code may have side effects. So tooling that we create for users is always running in code that we don't control. And so if the user is working on something that will perform destructive actions like removing files from their file system or migrating a database and dropping tables or anything of that sort, then we need to be very careful about the code that we're going to execute because it may produce a side effect that they are not expecting. But also executing code is much slower than just analyzing it statically. Even if your code is very fast for the context where it executes in production, for the constraints that the editor imposes on tooling, it can be maybe not fast enough. So if you have a type checking cycle or an analysis cycle that's taking a few hundreds of milliseconds, if the user's typing really fast and changing files all over, that may already cause some lag and lack of responsiveness. So what are DSLs? DSL stands for domain-specific language, and the way that I like to think about it is that it is a way for us to extend Ruby itself, so change the way that Ruby works. It allows us to do things that have dedicated syntax for in Ruby in other ways, using different types of syntax. For example, in this example coming from Rails belongs to, this is just a method call. We are only invoking belongs to in the post class, and that's it. But we know that from invoking belongs to, we are going to have new methods defined in our post objects, even though we're not actually manually defining them with the def keyword. So that's why I feel like it's a way of extending the language, a way of doing the same things that Ruby allows us to do, but differently. One way that we could implement belongs to, a super simplistic version of the implementation, is by using class eval. which evaluates any arbitrary string of Ruby code, and we can use that string of Ruby code to then define the methods for the reader of the association and the writer of the association based on the entity name that we are associating to. And of course, the bodies of the methods here are empty. We would need to actually implement the logic, but it's just for illustration purposes. The key to the DSL component here is the metaprogramming that we get from class eval. Invoking belongs to will mutate the declarations that are available in our code base. It will change which methods are available in the program. We're going to call this type of DSL declaration DSL, exactly because it will change the declarations that are available in the program. And to contrast with this other type of DSL here, another example coming from Rails. Validate takes the name of a method as a symbol, and you register those validations at the class level of your models, and Rails will automatically invoke those validations for you in objects of your model, in objects of the post class. The way that we could implement validate is we could have the method store the validations that you register in some sort of class level state. And then whenever is appropriate, like when you save a new record for post, we can then grab those validations that we registered, execute each one of them with dynamic dispatch by using send, and that will give the developer an opportunity to, inside the validation definition, add errors to the post object or do whatever is appropriate, and then the framework can decide what happens if there are errors in the post object that we're trying to save. So we can raise, return false, do whatever is appropriate. In this example, the key to the DSL component is the dynamic dispatch, the fact that we are sending a method that we don't initially know which one we're going to be invoking. And in this case, we are not changing which declarations are available in the program, but we are overloading the meaning of a symbol. From Ruby's perspective, the symbol is just a little piece of data, like a number or a string. But in this particular example, in this particular Rails API, it is overloading the meaning of symbol to be method names that are available in objects of the post class. We're going to call this one a call site DSL. And the contrast is just because the Ruby LSP gives us different APIs to handle each one of the types of DSLs. So what is difficult about analyzing these types of DSLs statically? There are multiple reasons, but I want to mention at least two here. The first one is the influence of runtime values and control flow in our code. So if we take another example here where we are defining a method dynamically with the name of the method being controlled by a variable, and then we are doing that conditionally on some other runtime value being equals to 5, well then it's very difficult for a type checker to be able to figure out what will happen in this case. We not only do not know the name of the method that will be created, but we don't know when it's going to be created. And this runtime value can depend on external things like a database query or user input or some sort of information in the file system. So there's very little hope of being able to analyze this accurately without extra annotations. And in addition to that, I want to also remember that we're always under the performance constraints of the tooling or the context where the tooling is going to be running, like the editor. So even in cases where you can argue that the piece of Ruby code we're analyzing can be fully understood statically, it may simply not be worth doing so. So for example, in this case, you could argue that this piece of code can be analyzed statically in its completion. You have create method, which always invokes define method, not conditionally, it's always guaranteed to happen. And we know that the first required parameter is always used as the method name without any modifications. And then in create hello, we know that we're always going to invoke create method with a string literal. So in theory, you have all of the information available here to analyze this piece of code statically. But the cost of doing so may simply not be worth it. You need to remember all of those bits of information so that the type checker can actually understand what's going to happen on each step. And even if you can't understand it, the method hello is only going to be available after you invoke create hello. So there's a lot of complexity that makes the performance cost grow. The reality is that type checking and statically analyzing Ruby is a constant tension between accuracy and performance. Even if we could create analysis that's like super accurate, if it takes 15, 20 minutes to run a single cycle of analysis, then the usefulness of it becomes very small. We need the tools to be performant. So we're always trying to find the balance between the usefulness that we can provide, the more accuracy that we can provide, and the performance cost. So now let's move on to the Ruby LSP and how we added new APIs to analyze these DSLs. If you don't know the project, the Ruby LSP is actually two different things. It is a language server for Ruby that adds extra features in any editor that go just beyond the basic editing of the code. And it is also a VS Code extension that adds features that are specific to VS Code. So here I have a few examples. The language server can show you documentation on hover. It can show you completion suggestions. It can also allow you to jump to definition on a constant, method, variable. And then examples of VS Code specific features I have here, our implementation of the dependency explorer that allows you to navigate all of the code defined in the dependencies of your project. And we are about to release our re-implementation of the test explorer that allows you to navigate all of the tests defined in your application. And then you can run them in 4 different modes of execution. The one that you just saw in the video is the simple mode, just run. You can run them in the terminal so that you can interact with the commands that we just used to execute your tests. You can launch an interactive debug session directly from the UI, and you can run them in coverage mode to see the results of coverage directly inside VS Code. We wanted the Ruby LSP to have as accurate as possible of static analysis. But the reality is, and understand DSLs like the ones that we just saw for Rails. But the reality is that creating new DSLs is something that's super common in the Ruby ecosystem, and we have so many different gems that do it. We couldn't possibly try to handle every single type of DSL within the Ruby LSP itself. It would be way too complex. So we wanted a way for the gems themselves to be able to teach the Ruby LSP how to understand the DSLs that they define. And this is done through our add-on API, which is an API for other gems to enhance the base features that we provide from the Ruby LSP language server. And the idea is for tool and framework-specific features and integrations to be added to the editor. So the Ruby LSP provides the base features for Ruby, for any type of Ruby code, and then DSL-specific things, integrations that are related to other frameworks, are all done via add-ons. The basic structure of an add-on is this add-on entry point class, and it has 4 mandatory methods that we ask to be implemented. Activate is the first one. It is invoked as the language server is launching, and it is an opportunity for the add-on to start any sort of background process, handle editor settings, anything that may make sense during initialization. We ask that they define the name method simply for presentation purposes. Very recently, we started allowing add-ons to export public APIs and to have one add-on depend on another add-on. And so in order to make that a little bit smoother, we started requiring that the version be defined so that we can then impose constraints on the add-ons. And the counterpart to activate is deactivate. When we are shutting down the language server, then we give add-ons the opportunity to perform any sort of cleanup or shutting down child processes, anything that might make sense. Before we move on to the specific APIs for DSL handling, we just need to take a look at how the Ruby LSP implements every one of its features, the architecture. And it is essentially a combination of 2 different patterns, the visitor pattern and the observer pattern. We essentially have this entity called a dispatcher, which visits an AST, traverses the AST, and as it is traversing, it will emit events for all of the nodes that we discover in a piece of Ruby code. And then other objects, the listeners, can then subscribe to the nodes that they are interested in handling, and they will be notified whenever we find those types of nodes in the code. So here's an example of a super simplistic listener implementation. We initialize it with the response builder. This response builder concept is what we use to collect contributions that are coming from multiple different listeners that will compose the final response that we return to the editor. And then with the dispatcher, with that entity I mentioned, we can register for which events we are interested in handling. So in this case, we are registering the object itself, the first argument there, self, and we're interested in handling method definition nodes, so whenever we find a new method definition in the code. And the last step is to define, well, what happens when we find one. And for this example, we're just pushing the node into the response builder. The way that we can use this listener is first we define the two top-level entities that control the composing of the response and the execution flow. So in this case, we're just going to be using an array for the response builder. In the actual implementation, it is more complex than that. And for the dispatcher, this is an object that we upstreamed a while ago at this point to Prism. You can use it for whatever purposes directly from the gem. And it gives you that ability to do the visiting of the AST with the observer functionality attached together as well. We can then attach our listener to those two entities so that it registers for the events and has a handle for the response builder. We parse any string of Ruby code that we are interested in analyzing to get the AST back. And then when we visit using the dispatcher, we are going to traverse the AST. The events are going to be fired, which then invokes logic in the listener. And by the end of the traversal, the response builder will be mutated with the, in this case, with the definitions that we found for methods. This architecture allows us to have pretty good separation of concerns. All of the features are implemented as separate listeners that have completely independent state and logic. But we also get really good performance because we can attach all of the listeners to the same round of traversal, and then we don't have to go through the same AST twice or 3 times or 4 times, depending on the number of features. We only go and traverse it once and capture all of the responses for every single feature. Okay, so now we are ready to start taking a look at how to handle DSLs and the new APIs that we are exposing. The first one is going to be declaration DSLs. We call this API indexing enhancements. Indexing is the process of discovering every single declaration in a code base. Since this type of DSL mutates which declarations are available, then it is contributing to the indexing process of the Ruby LSP. The API has 2 dimensions. You define an enhancement by inheriting from our base class, and then you can handle method call events, both the enter and the leave. Enter and leave is just so that you can accurately represent what will happen if you, for example, enter a new namespace and leave that namespace using a DSL. And the other dimension of the API is that every enhancement has access to our indexing listener, which then exposes the methods that you can actually use to inform the LSP about dynamically defined declarations. So add method will simply tell the LSP that, hey, here's a method that you may have missed because it's defined dynamically. You can do the same for modules and classes, but then one nuance is that adding a new dynamically defined namespace will advance the context of indexing to be inside of that namespace so that if we find constants inside of it or new methods, they will be automatically attached to that dynamic namespace. And then the fourth and last piece of the API is being able to leave that dynamically defined namespace so that we can have the correct flow for indexing in the end. So let's take a look at how we would handle the case of belongs to and inform the Ruby LSP of the methods that will be defined there. We can start by checking if the method that we just encountered during indexing is named belongs to, and if it's not, we are not interested in handling that method. We can then take the first argument, which is the entity that we are associating to, and here we need to check if the argument is actually there. Language servers usually see the code in an intermediate state as the user is typing, so it's very likely that we will see the code, the call to belongs to without arguments multiple times until the code is in its final state. And then if the name is already there, if the symbol is already there, we can take the association name by taking the value of that symbol, and we can then use the add method API to inform the index that, hey, there will be a reader for the association, and this is the name of that dynamically defined method. The only other part is adding the writer for the association. And there's only two differences here for adding the writer. Of course, the name is different because we have the equals, but also the writer accepts one argument, and so we have to define which signatures are accepted for that method. The Ruby LSP allows you to have multiple in case there are many different ways that you can invoke the same method, but in this particular example, there's just one signature with one required parameter. And that's already enough for us to be able to handle belongs to and tell the Ruby LSP that when we find that call, two new methods are going to be available inside of that post class, one for the reader of the association and the other one for the writer. Moving on to the other type of DSL that we talked about, call site DSLs. These are not a part of the indexing process because they don't impact the declarations that are available in the code base. So these are handled on a per feature basis. And they don't, not every feature makes perfect sense for these call site DSLs. So it's better that we handle them based on what we want to augment in the LSP. And the example we're going to see here is augmenting go to definition. The way that you can augment every single feature in the Ruby LSP is through these factory methods that are defined in our add-on class. And the idea of these methods is to create a new listener that will be taken into account when we execute that request. And you receive from the Ruby LSP everything that you need to hook into the response builder, into the execution flow through the dispatcher so that your listener is taken into account as we're running this request. So what we want to do here is we want to be able to command click to go to definition on the all is well symbol, on the symbol that represents a method, and end up in the declaration of that method. To do that, we're going to define our extra definition listener here for our add-on. In the constructor, we're going to essentially just save state that we receive from the Ruby LSP itself. We're saving the index, which includes all of the declarations that we discovered in your project. We save the response builder so that we can contribute more information to the final response. And the node context is another object that we get from the LSP, which has information around the place where the user is trying to go to definition for. And it'll be useful for the handler. In this case, we want to handle symbol nodes. If the user is trying to go to definition on a symbol, that's when we want to actually perform logic. And here's how we would define the handler for this. The first thing we want to do is we are not interested in any symbol. We are only interested in symbols that are being passed to a method call for validate. So we can use the node context to check, is there a surrounding method call that is surrounding this symbol node, and is that method call a call to validate? If that's the case, then we continue, otherwise we return early. We try to get the name of the symbol, the value of the symbol. Of course, here, if the user didn't finish typing, we need to account for that as well, so we return early if there's no name yet. If there is a name, we know which method name we are trying to find. And we also know that because validate was invoked, for example, in the post class, we know exactly which namespace we need to search for that method, which is given to us by the node context in this case. So we can use the index to resolve a method based on its name and the fully qualified name of the namespace that should own that method that you are looking for, and we're going to get back as the result an array of every declaration that we were able to find for that name within that namespace. Of course, when you're developing, you can do weird things like using a symbol for a method that has not been defined yet, so we need to account for that case as well, and return early if you didn't define the method. The last step is to take the declarations that we discovered that are related to the name of the symbol value that we are trying to jump to, and then format them for the editor and include them in the final response using our response builder. And in this case, we're just transforming the location of the declaration into a range, which is what the editor expects, and then we're creating this location object to push it into the response builder. And this is already enough for us to command-click on that symbol and land on the method declaration for all as well. And the API for the index of the Ruby LSP already takes other things into account, so like things like inheritance. If this method was defined in a module or in a parent class, that would also work. Since we announced the add-on API, we have had considerable interest from the community, which has been super nice to see. All of these add-ons, with the exception of the Tapioca and the Rails one, were created by the community and are not maintained by our team. In addition to contributing extra behavior to our base features, all of the intelligence that is contributed by add-ons is also available to any other type of integration that we use the Ruby LSP for. And I want to mention our latest prototype, which is an implementation of an MCP server that connects to the Ruby LSP to expose information about your code base to LLM and AI-related tools. If you're not familiar with the MCP, it is a server. It's actually quite similar to language servers in the way that the protocol is defined. And it allows LLMs, it allows language models to ask questions to that server to grab extra context. So in this case, we are providing extra context about your code base through the Ruby LSP, and it will take the contributions of all of the add-ons into account. So here's an example in Cursor. I asked it to draw a diagram, and it decides whenever it needs to ask for more information from the Ruby LSP in order to fulfill the task that the user has requested. And after it grabbed all of the information that it thought was relevant, it will then perform the task that you asked. And so the intention here is to expose information that would not be very easy for the LLM to discover, like what is the hierarchy of classes available, or what is the type of a variable, things that are not written down directly in the source code. Ruby is a very unique language, and of course that we can learn a lot from looking at what other gradual typing systems have done, but I don't think that it is enough, even though it is super helpful. I think we should experiment with new types of ideas that can try to account for everything that Ruby allows us to do. And I have some crazy ideas here that I frankly don't know if they are feasible, but I'll share them anyway. In the case of belongs to, could we have some sort of annotation where we inform the type checker that calling that method will produce new declarations that are dynamic? So things like new methods or new constants or new classes. And could we pass some sort of type parameter that can be used to then properly annotate the methods that will be defined dynamically, so that we could pass something like this, informing the type checker that belongs to will produce methods that are related to the user class. For the case of symbols that represent other things, like a constant or a method, could we have some sort of special type that represents that, so that we can have all sorts of type checking features, like type checking errors or completion or GOAT's definition, automatically available for those constructs? And in the case of instance variables that are not initialized in an object's constructor, so for example, in this case, where the instance variable user is always set by setUser and not in an initialized method, it is common, for example, if you're using Sorbet, to see errors related to the type checker thinking that the instance variable may be nil, because it may indeed be nil if you just create a new instance of the user's controller class. But could we try to inform the type checker that in this particular context, show can only be invoked after set user has been invoked, so that the type checker can essentially take the two bodies of the methods and glue them together so that the analysis matches what happens when we execute the code a little bit better. I think to have a better type checking experience in Ruby, correctness is of course important. We always want to be as accurate as possible, but not at the expense of usefulness. A gradual typing system is a tool, it's not a requirement, and we should try to be as useful as possible to users. And I also believe that we should optimize for the most common cases that people use Ruby for, providing escape hatches for the edge cases so that we can make optimizations for better accuracy in the cases that are most common for Ruby programmers. And with some innovation in our type annotations, I think we can get there. I think we can account for the dynamic nature of Ruby. Thank you very much.